Okay. So the next speaker of the meeting is Malcolm Fairbairn, Astrophysical Constraints on Dark Matter. 30 minutes plus 10.
Hey, can you hear me?
Yes.
Great. Okay, so thank you very much for the lovely invitation. I wish I was in this place, which looks very nice. It's lovely to see so many of you. It's boring not being able to see people in person, and it's starting to drive me crazy. I know that everyone's talking about carbon and how this is good for the environment, but I hope we get to see each other a little bit more in the next couple of years, because I'm getting bored of London. Okay, I also, given the context of the talks that we've heard, the very nice talks that we've heard, I wonder if I should have been talking about dark sector gravitational waves, but I'm not going to be talking about that today. I'm going to be talking about some astrophysical constraints on dark matter that my people have been working on over the past period. Okay, so we know there's 6 times as much dark matter as normal matter. This picture was supposed to be a lot more Instagram looking than it was, but this is actually 6 times. But no dark matter has been detected yet. There hasn't been a party. We're waiting for it to turn up. What can we find out about it without interacting with it directly? And that's what I'll be talking about today. So 3 methods we can use to constrain dark matter without seeing it. We can look at strong lensing probes of dark matter. We can look at the effect of light dark matter on nucleosynthesis, and we can look at galactic probes of fermionic dark matter. Okay. So let's start off with the first topic. We all know about escape velocities. We know that different objects have got different escape velocities depending on how dense they are, how deep their gravitational potentials are. Of course, we know that the Milky Way has got an escape velocity. And we know that dark matter must be traveling less quickly than this, since we know it's present in galaxies like the Milky Way. Okay. But we also know that there are galaxies that are smaller than the Milky Way with smaller escape velocities than the Milky Way. So we know that those galaxies have also got dark matter in them. Okay. So we know that dark matter is also present in dwarf galaxies, even ultra-faint dwarf galaxies, where there is very, very few stars because the gravitational potential is extremely shallow. And any kind of supernova or shocking knocks a lot of the baryons out of them. And so the remaining stars really are very good traces of the underlying dark matter. We know very well that there's dark matter in those objects, and we can measure the velocity dispersion of the stars. And in the process of doing that, we can solve the Jeans equation, which we'll be talking about a lot more later on. And we can figure out what the gravitational potential is. We can work out what the escape velocity is, and it's about 20 kilometers per second in a lot of these objects. So we know that dark matter can't be traveling that quickly. And the question we can ask ourselves is, how quickly was dark matter traveling in the early universe? We all know here there's slowly moving dark matter, where you've got structure formation on small scales, hierarchical structure formation, small things forming. And then as you warm up the dark matter and you go to warm dark matter and hot dark matter, you don't get so much substructure forming on small scales, because those small scale objects have got a lower gravitational potential. And if dark matter is moving too quickly, it won't be able to get captured and virialized inside those gravitational potentials. So you won't expect to see so much small-scale structure. Now, the problem is, so we already know that there is small-scale structure. I'll just stay on this slide for a minute. We already know that there are galaxies that are quite small that have got dark matter in them. But as I mentioned earlier, as you start to get down to dark matter halos, of course, the Milky Way has got a dark matter halo we think is about 10 to the 12 solar masses. Once you get back down to dark matter halos that are about 10 to the 9 solar masses, which we think there are some dwarf galaxies around the Milky Way with those masses, there's not many baryons inside them anymore, because you get supernova explosions and you get shocking and you knock all the baryons out of them. So you can't see them anymore. And once you get down to about 10 to the 8, 10 to the 7 solar masses, we expect, if dark matter is cold, we expect those dark matter halos to be there, but we don't really expect there to be any baryons remaining inside those halos, because any kind of shocking will just push the baryons out, okay? Any kind of star formation, any kind of pressure. But we also know that not seeing those small objects depends upon how quickly the dark matter is traveling in the early universe, whether the dark matter is hot or cold. And you can map it onto the mass of the dark matter. For example, if you make assumptions about whether the dark matter was in thermal equilibrium with the rest of the plasma, that will tell you how quick the dark matter was moving in the early universe. And so you see, if the dark matter is more massive, it goes out of equilibrium with a lower velocity, and so you get structures forming at smaller masses. But if it's less massive, then the smaller structures can't form anymore. So we have this problem. We would like to be able to map out this function and find out whether the dark matter does start cold or whether it starts with some kinetic energy. But we can't see these halos because we expect the smaller halos around 10 to the 8 solar masses and below. We don't expect them to have any stars in, so we can't make observations of them directly. So there's been quite a few people who've been trying to figure out how we can spot these smaller halos and find out more about particle nature of dark matter, in particular how warm it was in the early universe. And one of the most promising things that's come out of the past few years is this idea of looking at perturbations in streams. So around the Milky Way, we have these streams that are thought to be formed by the tidal disruption of things like globular clusters. And we get these huge streams which appear across the sky. And then what would happen is if we see dark matter halos go across those streams, they should perturb the streams, and they should knock out some of the stars in the streams, and we should see holes in the streams. So by observing the streams and seeing if they've got holes in them, we should be able to figure out if these smaller halos of maybe 10 to the 7, 10 to the 6 solar masses are there, even though we don't see any stars inside them, because they're whizzing around the galaxy, they're crossing these streams, and they're making holes in them but through their tidal interactions with the stars in these streams. So that's one method that people can use. That's not the method that I'm going to be talking about today. What we've been doing is we've been trying to look at lensing, okay? So to see if we can use lensing to observe these smaller structures. So it really does make a huge difference, because if you say, okay, well, I'm going to say that the smallest dark matter halo that exists in a galaxy, let's say we've got a galaxy with a virial mass of 10 to the 13 solar masses. So this is a rather large galaxy. And we say that there are only subhalos going down to about 10 to the 9 solar masses, and below that they don't exist because the dark matter is sufficiently warm that they can't form. Then you don't really get a lot of subhalos. But if you go down to 10 to the 8 solar masses, you start to see more and more subhalos. Down to 10 to the 7, you can see there's lots and lots. And because it's a power law, you get, powers more everybody's very careful about using the word exponential in these COVID times. Lots more smaller halos if you go down to smaller cutoff masses, okay? Now, we would like to use gravitational lensing. So we imagine that an object like this is a strong lens in between us and a galaxy which is much further away. And we'd like to ask the question, if we have a galaxy like that in between us and an object which is further away, which is creating a strong gravitational lens, can we tell the difference between a situation where there is lots of substructure going down to a small mass cutoff, or there's not so much such substructure going down to a higher mass cutoff? So for example, the first thing we need to do is we need to simulate objects like this. So we've got a lens in the middle of this plot, and we're moving the source relative to the lens, and you can see as it goes across, we get a nice feature in the middle which represents a strong lens. What we do is we simulate these kind of images for lots of different orientations of the source relative to the lensing object, but also different lenses that have got different amounts of substructure going down to different cutoff masses in them. Okay. Now, at the top, you've got 4 images which correspond to lensed images where the lensing object has got substructure down to 10 to the 9 solar masses, okay? And at the bottom, you've got 4 images where the lensed images go down to 10 to the 6 solar masses. Now, can you tell the difference between these? I can't tell the difference between these. But of course, we do what everybody does these days. we get a computer to see if it can tell the difference between these. So we use machine learning, in particular convolutional neural networks, to look at these images, because these things are particularly good at looking at images. And I have a student, Sridevi, who's actually finished now, but who used machine learning techniques to see if she could tell the difference between these different situations where you have more or less substructure. The short answer is we can. So what you're looking at here is, if you look at the graphs along the top, you see these are different ranges of halos. So we've got the lower bound of subhalo mass range. We've got 10 to the 6, 10 to the 6.5, 10 to the 7, 10 to the 7.5, 10 to the 8. And you see this is actually where we put in simulations that include halos down to 10 to the 6 solar masses. And our machine learning algorithm has classified them inside that category quite successfully. So it's successfully getting them in the right box. Whereas here, when we simulate objects that only have substructure down to 10 to the 7.5 solar masses, again, it's usually getting them in the right box. And this is this sort of heat map here is an indication of I think the x-axis is what we wanted to get out, and the y-axis is the correct interpretation, showing that we're on the diagonal, which means that we're correctly identifying precisely what mass these subhalos are going down to. So what this is telling you is that essentially we can figure out to some degree how much substructure there is in these lensed objects using machine learning. Now, what we're trying to do now is generalize this and try and make it more robust. So we're currently working to improve these initial results and make them more general. But there are other people working on the same subject using different techniques. At the moment, we're quite optimistic about how this is going. So we're hoping that this strong lensing stuff will be able to eventually tell people. Now, tell people the difference between whether we're looking at halos with a spectrum of subhalos that goes down to very, very small mass or doesn't go down that far at all. Okay, but it might be, there's another sort of frontier which we can't. So much for substructure. Okay, we'll sort of come back to that later on. But there's another frontier that obviously we haven't seen any dark matter in direct detection experiments. Now that could be because the dark matter does have masses of 100 GeV, and we know that it's moving around about 200 kilometers per second where we are, but it might not be interacting with us. But it could also be due to the fact that the dark matter mass itself is too small. In which case, when it does hit our dark matter detectors, because we know no matter what the mass of the dark matter is, it's traveling around 200 kilometers per second. If it's sufficiently small, it won't have enough kinetic energy or momentum to impart enough recoil energy in the detector to make it go bing, so the dark matter detector won't do anything at all. So we have to look at ways that we can investigate lighter dark matter. And one of the ways that we've looked at that is with my collaborators, James Alvey, Nashwan Sabdi, Miguel Escudero. Oh, and I've forgotten to put Diego Blas here, but Diego Blas as well. We wrote a paper together to see how these light dark matter particles might be able to affect nuclear synthesis, okay? Now, if the dark matter is too light, it can change the prediction for how much helium and deuterium is left over after the Big Bang, okay? So in particular, we're talking about dark matter particles that interact, that annihilate to either form neutrinos or form electrons, okay? And so the way that the temperature of the neutrinos and the temperature of the photons evolves in these two different situations depends upon these extra terms which are added. It also depends upon these pressure interaction terms. These are how the masses of the particles are changed due to QED temperature corrections. But what we're really interested in here is the extra introduction of energy due to the dark matter particles annihilating into standard model particles and changing the way that the temperature and time relationship changes during nuclear synthesis. So here's the normal standard model expression, But in addition to that, we could have dark matter particles that are annihilating into standard model particles. And these have the effect of changing the relationship between temperature and time. And of course, that can have various effects on Big Bang nucleosynthesis. If you change the relationship between temperature and time, you change the neutron to proton freeze out, the ratio of neutrons to protons that freeze out, of course, because that depends upon when the weak interactions freeze out. So if you and that depends upon the Hubble expansion rate relative to the temperature, so you change that. If you also change the relationship between temperature and time, you change the point at which photodissociation of deuterium stops, and you can't really start to form helium until you've stopped photodissociating deuterium. And then, of course, you can also inject energy into the plasma after some of the nuclear reactions have taken place, which will reduce and dilute the number density of the particles that are created. So these three effects are the main three effects that you have to take into account. And we did so. You can see how dark matter, depending on its mass, and you can see for how it changes the number of effective degrees of freedom, depending on the kind of dark matter that's interacting. And you can see how it changes also the abundance of helium and how it changes the abundance of deuterium. Okay. Now, in order to do these calculations, we used somebody else's software. We used the PRIMAC code, which is state-of-the-art Big Bang nucleosynthesis code, although there are other nucleosynthesis codes are available. It's the good thing about this is it's got accurate predictions for helium and deuterium abundances, up-to-date nuclear reaction rates, and finite temperature corrections. I've put and deuterium there, I've just noticed. And then we try and fit the chi-squared to see if we can reproduce the observed values of the helium and deuterium abundance. We also take into account constraints from Planck on omega B and what have you. So, and we were able to use this to get quite tight constraints on the mass of dark matter, okay? So, and these constraints are comparable with other constraints that you can obtain. So for low mass dark matter that's interacting with standard model particles, you have to be quite careful that you don't mess up the predictions, the successful predictions of Planck, but also the predictions of Big Bang nucleosynthesis. Okay, how are we doing? Right, but then you can talk about light dark matter and see if you can constrain it in other ways. And for example, what I've just told you about is dark matter which is in the MeV range, but dark matter which is interacting with standard model particles. Of course, we don't know if dark matter interacts with the standard model particles in any strength in such a way that we'll be able to observe it. We're just trying to push back the parameter space wherever we can. Okay, but we could just say, well, what if the dark matter is made out of fermions? We know that if it's made out of fermions and it's too light, that you can't get too many of these guys in the same place at the same time. So can we get a limit from the observations that we make of the Pauli exclusion principle, from the Pauli exclusion principle? In particular, can we look at small galaxies that have quite dense cores? Now, the reason why these galaxies have got dense cores is because they formed earlier in the universe. Smaller halos form earlier in the universe at higher redshifts, and they retain a kind of memory, in a sense, of the density of the universe in which they were formed. But at the same time, in terms of they've got high phase space density because they don't have a deep gravitational potential well. So when you look at the virial theorem, the kinetic energy is less. So while they're denser in physical space, they are less, they've got less momentum. And so consequently, the 6D phase space, they're really quite a lot denser. So what we'd like to do is we would like to look at dwarf spheroidal galaxies. And because these ultra-faint dwarf spheroidal galaxies in particular, and because these galaxies don't contain many stars, we have to look at them the ones that are quite close to the Milky Way, because these are very dim objects. Now, of course, people have done this in the past, so why do we think that we can do better than anybody else? Well, there are new techniques that have been developed, and they've been developed by many people over the years. Mike Merrifield was one of the people who was most interested in this kind of thing. We started to look at this. I started to look at this with one of my PhD students quite a long time ago, nearly 8 years ago, Thomas Richardson. And I'm going to explain to you these new dynamical tests and how they can constrain better the gravitational potential of these smaller objects. So here's some of the dwarf galaxies that are flying around the Milky Way. These are not very far away, right? So the dwarf galaxies, as I've already said, they're heavily dominated by dark matter. So the work I'm talking about now was again done with James Alvey and Nashwan Sabti, and Diego contributed. But we didn't have Miguel Escudero on this. This is with a group from Leiden, and you know quite a lot of these people quite well. I know that quite a lot of you know Alexei Boyarsky and Kirilo Bondarenko and Victoria Tiki. And then also we got some help from Justin Reed at the University of Surrey and his student Matthew Orkney, and they do astrophysics. They are experts in the modeling of these dwarf galaxies. And these are the galaxies that we considered because we've got nice data for them. Now, what's this trick that we use in order to try and measure the dark matter better in these galaxies? First of all, let me explain what people normally do. Remember, we've got Gaia now, and you might think, well, Gaia is really good because we can take parallax measurements so we can see the proper motion of stars. Gaia is only really supposed to work for the local 5 kiloparsecs. These dwarf galaxies, some of them are 100 kiloparsecs away. So they're too far away to get very good parallax errors, and they're too far away to get proper motions. You might be able to get some upper limits on proper motions from Gaia eventually, but really Gaia's not designed for these kind of objects. So you can't really look at the motion from left to right of these stars on the sky, and you're really restricted to the line of sight velocity dispersion. So what we can do is we can look at the stars inside these dwarf spheroidal galaxies, and all we've got is the line of sight velocity dispersion, okay? Now, just an aside here, it is possible, and there was a proposal which I was involved in a few years ago for an experiment called Theia. Now, don't confuse this with the neutrino mass experiment called Theia. This was a space-based telescope that was essentially going to be Gaia on steroids, if you like, okay? It was going to be super Gaia, so Theia or something. Theia is the daughter of Gaia, as far as I understand. I'm not classically trained like Boris Johnson, but anyway. If you look at these objects that are far away, if you have an object like, if you have a spaceship like Theia, it can train in on these objects and look at the parallax and the proper motion. It can't do the whole sky like Gaia can. Unfortunately, that proposal's not yet been successful, although I understand there's some interest in Japan on picking up the idea and running with it. But for the time being, we really have to rely upon line of sight velocity dispersions for these stars. So we can get those because people can do spectroscopy. It's a difficult job, but some people dedicate a lot of their time to doing that. And so we have line of sight velocity dispersions for the stars as a function of projected radius from the center of these dwarf spheroidal galaxies. And then we have to solve the Jeans equation. This bit here on the right, it's GM over R squared. It's just the gravitational potential. And then we've got the radial velocity dispersion, which we can't measure, and this thing called the beta anisotropy parameter, which is the ratio between the tangential velocity dispersion and the radial velocity dispersion. So this is in the frame of the galaxy. At each radius, there's a tangential velocity dispersion and a radial velocity dispersion, and the ratio between them is given by this parameter beta. Now, the line of sight velocity dispersion is related to beta and sigma r. So it's related to both of these things. And of course, we don't know what beta is, okay, because we can't go to the galaxy and measure it. And we don't have any proper motions. So we have to marginalize over beta. And this leads to this famous beta degeneracy, which is basically that the enclosed mass inside these dwarf spheroidal galaxies is only really constrained at one radius, which is the half-light radius. And if you choose different values of beta, you get different densities as a function of radius. You get different masses as a function of radius. And although they all pass through each other at one radius, you can't really tell what the density is at the middle. And we'd like to know what the density is at the middle, because that's where the phase space density is going to be highest, and where we would like to find out if there's any constraints on fermionic dark matter. So what this extra work that we've done, working on the work of Merrifield and Kent with my student Tom Richardson, which was then further taken by Justin Reed, and other people have worked on this as well. Is we're just taking, we don't take only the second moment. If you look here, we're just dealing in second moments in the Jeans equation here. We look at other moments as well. So we're interested in whether the line of sight velocity dispersion is leptokurtic or platykurtic. In other words, we're looking at ratios between the fourth order moments and the second order moments, okay? And so we introduce these virial shape parameters that depend upon the fourth order line of sight velocity dispersion, okay? And it turns out that this depends in different ways upon beta and the radial velocity dispersion inside the dwarf spheroidal galaxies. And the way, because it depends in different ways, we're able to constrain the density as a function of radius in a different way. So we can marginalize over beta using, we use some priors from simulations, but they're quite wide priors. And so we can use this to break the degeneracies, and we can obtain good density profiles for the dark matter in the stars. The dark matter as a function of radius inside the dwarf galaxies. And here's the density of dark matter inside these dwarf galaxies, once we've taken into account these higher order corrections to the Jeans equation. And then we can start applying this. We then have to figure out how quickly the dark matter would be moving. So we have to solve the Jeans equation again inside this gravitational potential for the dark matter. And then we have to make some assumptions about beta, but we allow beta to vary quite a lot. And we use priors from simulations for that. And then we can get limits on the mass of the dark matter. So if we just assume, you can do this in various different ways. You can just use Pauli's principle, which is kind of model independent, and that straight away gives you a constraint that the dark matter has to have a mass bigger than 0.27 keV. So the other thing that you can do is you can assume particular models of fermionic dark matter. So for example, sterile neutrino models, resonantly produced sterile neutrino models. These are a bit different because you start with a different phase space distribution of dark matter in the early universe, and then you use Liouville's theorem to work out how that maps onto the phase space density inside this gravitational potential. And then you get slightly different constraints. And you can see from this picture here that we get constraints on the parameter space for sterile neutrinos. Now, these are not as strong as the Lyman alpha constraints by a factor of a few. But you could argue, depending on how you feel about the Lyman alpha constraints, that these situations are much more under control because we're doing this using dwarf galaxies that we can actually see right next to the Milky Way, as opposed to something in the early universe. I'm not sure how far I agree with that thing that I just said, that argument, because I think the Lyman alpha constraints are pretty good. But it is nice to have another complementary constraint. So these are very, very robust. They're actually, I'm very confident about these constraints. They're actually not as strong, Dimitri, they're not as strong as some previous constraints which have appeared in the literature based on dwarf galaxies, but I think they're pretty good. Right, so I'm going to summarize now. I think I've been talking for half an hour. We are, I've got that Zoom thing that's on top of my first conclusion. We're using different approaches to learn more about dark matter. We're using strong lensing to see if we can detect substructure with machine learning. We're looking at Big Bang nuclear synthesis, change to thermodynamics due to light dark matter. And we're using new techniques to study dwarf galaxies that can give insight to dark matter, which gives us a constraint on the mass of fermionic dark matter. So my argument has always been that wherever we find a way to constrain the nature of dark stuff, we should investigate it as hard as possible and push back on parameter space wherever possible. And so that's what we've been doing. Thank you very much for listening.
Okay, thank you very much. Questions, please, or comments? Peter?
Malcolm.
Yeah.
For your lensing story.
Yeah.
I just did not understand this machine learning figures which you have shown. You obtain them just from one image, or
No.
Or you have many images superimposed?
We generate about 100,000 images.
So you need to observe 100,000 of these spots with different shapes, etc., and then you can feed it to your trained network, and then you get the answer. Is that the story?
Yeah. Well, no, I mean you can get the more data you give the machine learning algorithm to train on, the better fit you get. Okay, so you can do it probably with 1,000 images if you wanted to, but it wouldn't be as good.
How many we have by now?
Are you talking about actual data, or are you talking about simulations that I've got?
Yeah, you were using simulations, I suppose, but how many images do we have now of this bright patterns, which you could think of feeding to your network? I mean, what is the scale of all this process? Do we need to wait hundreds of years before we accumulate thousands of this, or?
So that's a really good question. So I think people at the moment are at the stage in this industry of figuring out how practical this is all going to be. So different people are using different approaches. Some people are looking at rings, in particular, sort of just studying the nature of rings themselves, as opposed to looking at overall images and just letting a neural network do the same thing. And they're trying to look at the fuzziness in the edges of these rings and then compare it with data. So I think the program is complicated because you also have to be aware of the fact that there will be features in the data based upon features in the source image. Okay, so there are lots and lots of strongly lensed images of galaxies, if that's what you mean, Peter. But what we're currently figuring out is what resolution we have to go to in order to have more success when we generalize different features of the source and the lens. I'm not sure I answered your question, Peter.
So in principle, you can pick the already existing images of the galaxies, sort them out, throw out what is.
But you can't train with those, Peter, because you don't know how much substructure exists in them.
Don't you have to train on the simulation and then feed it to the real data to tell you what is how well it corresponds to your simulation, or what's
that's what we ultimately have to do? Yes, yeah. So some people have already claimed to have done that for multiply imaged objects. Okay, but in principle, you would like to just give your algorithm a sample of lots and lots of different strongly lensed images, and then based upon the redshift that you have for the lens and for the source, it could figure out, hopefully, by looking at a catalog of images, what the structure was, what the cutoff in the structure was at low mass.
So the bottom line, is it a matter of a couple of years, or is it a matter of tens of years where one can realistically hope to get something definitive from that?
I would suggest that my guess would be that people will start to come up with constraints increasingly in a couple of years, but I think that other people won't take them seriously for a few more years after that. So I would suggest that this is sort of an industry that's in its infancy. There are multiple approaches, and people have already started to get constraints from these from these strong lensing analyses. But I would say that people are going to have to be sure that everybody knows what they're doing with their systematics before people take them seriously. So I would say that the stuff will come in, but people won't believe it for a few years until it's been sort of identified by multiple different approaches.
Okay, thanks.
Mm-hmm.
So other questions or comments? Michael, let me ask one about this dwarf galaxies limits. I mean, the number looks exactly, I mean, not exactly, but more or less the same as the original limit from, from the Pauli principle. Yes, at the level of 1, 2, 3 hundredths of EeV. But as I understand, what is the advantage of your work, your method, is that now the extraction of limits from observations made by astronomers are now more reliable, more robust. Yes, that is the point.
That's what I'd argue. I would argue that some of the previous analyses were a bit optimistic. So when we sort of look,
the original, the original paper where people suggested this to use the Pauli blocking to use the limit to place the limit on the, they more or less
sorry, Gunn and Tremaine.
Yeah.
No, exactly. It was different. I can't remember what the number was, but it was significantly different. Because they were using much bigger galaxies, Dima, right? So I think they actually used the Milky Way, right? So they didn't have anywhere near as much phase space density to work with. So it was significantly different. Now I think what you should compare it to is the number that Alexei came up with maybe 10 years ago or something. We're getting similar numbers to that.
Look, the number on your slide here, 0.27 keV. I mean, this number is very similar to what people obtained originally. And well, when you use it for dwarfs, that people discuss something like 0.7 or something like that, just from Pauli blocking, nothing else. I mean, no any the sophisticated things about the space density. Yes. Yeah. No, I understand your point about this specific model, like sterile neutrino with this enhancement due to the resonance production, and that's these things. Okay, but here is, I mean, this I would say the numbers more or less the same. But okay. Other questions or comments? If not, let's thank the speaker again.
No, it's not. It's a factor 200 different from the original Gunn Tremaine bound. I think you're wrong.
200?
Yeah.
200?
I think the Gunn Tremaine bound was an EV. It wasn't a KEV.
No, it's not a KEV. It's 0.3 KEV. Okay, so it's 300 EV.
Yeah. So I think the Gunn Tremaine bound, the original one, was about 1 EV.
No.
Well, let's agree to differ.
No. 1 EV. No. Look. 1 EV is not enough to form the dark matter. You see, 1 EV is not enough. You need more EVs to form the dark matter. Okay. Okay. If not, then thank the speaker again, and let's move to another. And
I have a comment, Dima. I have a comment.
Sorry?
I found the Gunn Tremaine limit. It's 1.2 electron volts. So.
Okay.
Yeah, and it has no any sense because it's not enough for this fermion to form the dark matter in the universe.
Well, take that up with Gunn and Tremaine in 1979.
Or not. Yes. Okay, any other comments? Yeah, this one.
And of course, the phase space, the mass goes like the quarter power of the phase space density, which is why it's so difficult. So I agree that a factor of 100 is not impressive, Dima, but it's a factor of like 10 to the 4.
Yeah, but formula number 6, it's something like 100 electron volt. What is it?
No, I think they get it up to about 30 in this paper. It's very difficult yeah. No, I take your point, Dima. You're not impressed by our results. I'm just saying that you got the Gunn Tremaine limit wrong. That's all.
Yeah, but then this is the phase space density. Okay, I mean the formula number 6 is the phase space density limit. Okay, and the formula number 5 is just the Pauli principle. Yes.
Yeah.
Okay, so this is the factor of 100. Wow. Okay. Yes. Thanks.